today's talk, I'm going to present my work on neural network verification, where we want to formally prove the trustworthiness of a neural network. So we all know neural networks have achieved great success in many fields, but when applying neural networks to real-world tasks, we often want to know if they are reliable enough to be used for some mission-critical tasks. For example, it's not uncommon that a autonomous driving system utilizes neural network-based computer vision techniques to detect road signs, pedestrians, or other important objects around the car, and a failure of detection can lead to death. And similarly, in medical system, a malfunction of the equipment or wrong diagnosis may also kill people. In security systems, we may also ask a neural network to detect suspicious object and also detect malware, detect intrusions, and evasion of surveillance can cause loss for this for the object under protection. So the big question here is, can we trust neural networks that make sure it behaves predictably and also reliably when it's applied to these very critical settings? So unfortunately, the answer is mostly likely no, because many researchers have found that neural networks can be quite unreliable under many realistic scenarios. For example, in a very recent paper at ICCV 2021, researchers showed that by changing just the illumination on the stop sign using a projector, they can actually trick the road sign detector, and the stop sign can be detected as a speed limiting sign. So that will cause a major failure of a computer vision based self-driving system. This can also lead to critical consequence. If we blindly just trust the outcome of the neural network. So in medical applications, people found that a simple rotation of a medical image may actually flip the outcome of a neural network from benign to malignant for no reason. And in that case, and also in the case of medical records with text, if you just replace some words with their synonyms, such as alcohol abuse to alcohol dependence, then surprisingly, outcome of the network can actually change, which may eventually lead to misdiagnosis. So these inputs that cause these failures are often called adversarial examples. And to confidently use neural networks in these critical applications, we hope to use formal methods to guarantee the behavior of the neural network so that this case shouldn't happen. So this leads to the neural network verification techniques. The goal of neural network verification is to formally prove some useful properties such that we want the neural network to have these properties so we can formally trust them. So for example, if our desired property is robustness, then we hope the model predicts the same class for the original image as well as the image with a small perturbation noise. In the case of adversarial examples, a model is not robust to these small perturbations and can actually predict the surprisingly wrong results. And we must prove that it won't happen for a safe model. So if other desired property is fairness, for example, in the case of a AI-based resume screening, we hope the AI doesn't have a gender bias and give the same outcome if the gender is the only factor that differs in the resume. Additionally, for example, in finance, if we are using machine learning to decide how much loan we should approve for an applicant, it makes sense that when the income of the applicant increases, while keeping other factors the same, the approved loan amount should also be monotonically increasing. Otherwise, it's really hard to explain what the model is doing and what is going on. So monotonicity is also a good property we want to have sometimes. And lastly, even using machine learning to control critical equipment such as vehicle or aircraft is also important to guarantee the correctness of the behavior. For example, in the airborne collision avoidance system, the input of neural network-based controller can be the velocity and the angle of attack of the intruder. And we must guarantee that the controller never issue commands and may make the two aircraft collide. In this talk, I will mostly focus on the robustness verification setting, but please keep in mind that neural network verification can be useful in many different scenarios. So one important fact in verification is that verification requires a formal proof to show a property holds. For example, in the robustness verification setting, we need to know that we can prove for any noise that you can potentially add to the image, such as for the robustness verification setting, we actually want to prove that for any noise you want to add to the image, such as this bounded by a LP norm bulb, you can actually cannot change the noise, the prediction of the model. In contrast, there are many other allocell attack methods that can heuristically find a allocell example that makes the model fail. However, even if all these attacks cannot succeed to attack this model, we still cannot verify the robustness of the model because there are open cases where allocell examples are missed by an attack. So even if you cannot attack the model using any known existing attack, you still cannot guarantee the model is safe. So the model cannot be attacked is different from it is being verified. So a formally proven model will always predict the same label, no matter what attack you're using, because I can guarantee that for any X inside this perturbation set, which is a lot of perturbation the attacker can add, you can ensure your model will predict the same label always. For example, in this case, it's always gonna predict dog with any added small noise. And we can guarantee that your model is probably robust, not just looks robust by using some heuristic attacks. So to get you familiar with the basic formulation of the problem, I've introduced a very simple example on robustness verification. But keep in mind, verification can also be applied to many other settings as long as we can get a mathematical formulation similar to what I will present here. So consider we have a binary classification classifier neural network, and the input is some data point X. And so the output of the network is gonna be a score of X for X. For example, it's 1.2. That means, for example, this class is a dog. For example, here our positive example can be a dog, and negative example can be a cat, for example. Suppose originally we have a positive example. That means fx is greater than 0. We have a cat image here, and can we verify this property such that within this perturbation set C, so this can be a small neighborhood around an input image. We want to show that the model always predict cat. If we can show that, actually we can formally verify the robustness of the model. So, but we must prove that for any potential image within this box, so this box means the perturbation set, which is the allowed perturbation from the attacker, and is a threat model in our setting. We must consider all possible attacks within this allowed range. And in that setting, so what's going to happen? If we consider all the potential input within the set, then the input of the network is not a single image anymore. This is actually a set of images that contains all the images within this perturbation set. And we want to show that actually for all the possible input in this set, the output is gonna be positive. That means it's a positive class of cat. So in this case, if we find that if for some reason we can enumerate all the possible input within this region, we can actually find the range of the output, because the input is not a single image anymore. So output is just a range of scores rather than a single score. We will be able to find the worst case scenario of the classifier under the set of input. For example, if we know the fx is going to be between 0.2 to 2.2, and the worst case for any input within this perturbation set, it's gonna be 0.2. That's still a positive number. That's still the model still predicted a cat. So even in the worst case, it's still a cat. You know that no one can really change the outcome of the classifier for any image within the perturbation set. So the basic formulation looks like this. Assuming we have a positive example, we want to find the minimum of the fx given any allowed x within the perturbation set, such as the set C here. And the C here usually actually you can define C as a general set, but usually for mathematical convenience, it's usually defined as the LP norm ball around x0, but we can do other definitions as well. But for simplicity, let's assume it's just, for example, a L infinity ball around x0. And if after you solve this problem, you actually find the worst case x star and f star within this perturbation set, and you can just check the worst case f star. If f star is less than 0, then you know you can actually flip the label from positive to negative. And so the model is not robust against other cell perturbations. However, if I can show even the worst case is positive, then I know the model is probably robust. It looks like just you can just solve the problem with a simple optimization. So is it really hard? The answer is actually yes. If you look more details into its optimization problem, you'll find that it's actually the problem has non-convex constraints. It comes from here. So assuming here the notation is like the Z is a pre-activation after a linear layer, and Z hat is a post-activation after the ReLU layer. And the output of the network is just suppose it's a binary classifier, so it's just the last layers, last layer feature is going to be the output. And in this constraint optimization problem, we define the pre-activations as the post-activation times some weight matrix plus some bias. And the post-activation, for example, the value after ReLU is gonna be just equal to the value before ReLU applies some apply some activation function. And we also have a constraint for the input, which we restrict the input to the set C. So this is actually the optimization problem we want to solve. We found here, we found that the first constraint is actually a linear constraint, so actually it can handle easily. And the input perturbation constraint actually, if you consider just LP norm ball, then actually it's also a convex constraint. But the issue comes from this constraint where you have activation functions. So all the neural network verification algorithms actually differ in how they deal with these activation functions. So if we look at this constraint says that the pre-activation value and post-activation value need to be on the graph of the ReLU function. So as you can see here, this graph contains two straight lines, and that's actually a convex set. So on this 2D plane. So and people also show that in general, the neural net verification is NP complete because of we have this non-convex constraint here. But we still have ways to deal with it. For example, we can use a integer programming approach to encode the ReLU neuron. So let's say for each ReLU neuron, we create an integer variable a, which can be either 0 or 1, a binary variable. And if a equals to 0, I can use some commonly used tricks in integer programming to make this constraint added to the formulation. So the hat equals to 0. That means when a is 0, then the ReLU is on the negative set. When a equals to 1, we can add this constraint to the formulation, and that means the ReLU is active. It's always act like a linear function. So if you do a mixed formulation like this, you have a binary variable to encode the neuron status, then you can actually use the MIP solver to solve the verification problem. You can actually get the exact value of f after MIP solver finishes, but the issue with this approach, of course, is MIP solver is really slow, and you cannot really use it for the case you have thousands or tens of thousands neurons, so they'll have thousands of these binary variables, and the MIP solver is kind of like useless in that case because it runs so slow. And the second approach is to relax the MIP problem to a linear programming problem. So if we cannot solve the meep problem and it's so slow, we can usually what people do is just do a relaxation and relax the meep to a linear programming. So you can solve it in a reasonable within a reasonable time and scale up the verification. But actually, if you use this approach, you only get a lower bound of f star rather than the true f star. So the true f star is unknown because you can only get by a meep solver. Let's assume we are not running meep solver, then we are only get a lower bound. But if this lower bound is greater than 0, I know that the f star is also greater than 0. So we know the model is still provably robust, even if you don't know the ground truth f star value. But the issue is, if you after you do this all the relaxations from meep to linear programming, the lower bound tend to be loose, especially if you have a lot of neurons. That means the lower bound can be much less than 0, so it won't helpful for full verification. If the lower bound is less than 0, then the true f star value can either be positive or negative. You don't know. So in this case, the verification is incomplete. That means you for some scenarios you cannot tell the answer. You don't know if this is verified or not verified. You don't know. So this is called incomplete verification. So the goal of this talk is to develop to show you the algorithm and tools that we developed to help us efficiently to verify neural network properties efficiently, also gain the trust for the black box. So the strategies we used to develop algorithm, including using very efficient bound propagation methods to replace the LP or meep solver. And we use GPU acceleration, which is never possible when you're solving a meep or LP using these commercial solvers. And also our bounds can be optimized quite cheaply by using gradient ascent, which allows us to improve the bounds within a very short amount of time. And also we apply the branch and bound techniques to make our incomplete solver to a complete solver to further increase its power. So the work presented by this talk are from these papers, and all our work combined together becomes alpha beta ground verifier, which is a winner of the verification of neural network competition in 2021. So let's start from the most basic paper. The paper I published in 2018 is using the bound propagation method to give you the lower bound of f star, so to do the incomplete verification. Just to remind you, if somehow we find the lower bound is greater than 0, then we can conclude f star is greater than 0. So we know there is no adversarial example in your classifier. So in that setting, so I developed the algorithm called Cron, which can actually turn a highly nonlinear and convex function fx into a linear function. And we know that we basically use the linear lower bound to bound its function. And actually within this perturbation set C, you can easily solve the minimization of the linear problem. And that is also a lower bound of the original problem. That's a high level idea we're using. So when we're using linear functions, because assuming we don't have ReLU neurons, for example, we just have a 3-layer network, we don't have ReLUs, then we can just merge all the weights together into a single vector. So in that case, actually, we can solve the robustness verification problem easily because we can just use Holder's inequality, which can be applied to any LP norm perturbation, and I can compute the worst case f star. This is pretty simple. But the issue with the ReLU network and other networks with activation functions is that because of these activation functions, you cannot merge weights like this. So you have to do something more fancy. So if we just focus on the ReLU case, then we can observe that the ReLU activation function can be actually split into 3 cases. If we know that the input of the ReLU is actually always greater than 0, for example, if we know the input bounds of the ReLU function, which we call the pre-activation bounds or intermediate layer bounds, if they're both positive, lower bound and upper bound are positive, then we know the ReLU actually becomes a linear function. If they're both negative, we know the ReLU actually becomes 0. So you can actually delete that neuron from the network. It won't affect anything. So if these two things happen, then we know actually we know how to deal with ReLU because they are already linear functions. And the tricky scenario is the so-called unstable ReLU neurons, where the ReLU can either be inactive or active depending on the input range. So in that case, we must relax the function. And the way we relax the function is for a given ReLU neuron. If we just take a look at a single ReLU neuron, we can actually use two linear bonds to bound this ReLU function. So high-level idea is to use linear bond to bound the function, and somehow we can propagate this linear bond through all the layers, and you still get you can still get a valid linear lower or upper bounds to bound the entire neural network function. So how we achieve that? Suppose we have a simple three-layer network here for demonstration, and we have three weights W1, W2, and W3, and our goal is to get a lower bound for fx, given the perturbation x belongs to a set C. And in the Quark algorithm, what we are doing is to propagate a linear lower bound for the output neuron with respect to hidden to input neuron. I will show you how that linear lower bound works. So initially, we want to find the linear lower bound from fx to z3, but fx just equal to z3. So you have actually equality here. There's no inequality. And now we propagate the linear relationship from x to z hat 2, which is post-activation after the second layer. And by definition, you know fx equals to w3 transpose z hat 2. This is just by plugging the definition of the network, and nothing happens. This is still a equality, and there's no inequality here, but this is a special case of a linear lower bound. And the tricky thing comes from a ReLU neuron, where when you encounter a non-linear function like ReLU, you have to propagate the inequality from z hat 2 to z2 and still maintain this inequality. How do we do that? In high level, we represent the ReLU function as the diagonal matrix, which reflects the relaxation we used in our algorithm, and we choose this diagonal matrix such that this lower bound holds. So how do we choose that? We just talked about we can use one linear upper bound and one linear lower bound to bound the ReLU function. Suppose the slope and the intercept of the linear lower and upper bounds are just A and B here. We have one set of A for lower bound and one set of A for upper bound. So they're just linear functions. After you know the L and U, you can actually you can compute this A and B. So this you can do this in closed form solution. It's quite easy. And after you linearly bound the ReLU function by a linear lower bound and a linear upper bound, the next step is trying to lower bound this function W3 hat times ReLU applied to the Z2, which is W3 hat dot product between the Z hat 2. And this is dot product, so if we just take a look at each term, this is gonna be one element of WG3 times the ReLU's output of the previous layer. And if we want to get a lower bound for this term, we can lower bound each term individually. So how to lower bound each term individually? When this WG, G's element in W3 is positive, then we take the lower bound of the linear relaxation. When WG is negative, then we take the upper bound of the ReLU relaxation. So overall, we can lower bound this function by taking either the lower bound or the upper bound of the ReLU relaxation, depending on the sign of the weight matrix. That's gonna give you a worst case scenario estimate for the lower bound. So because we know both the lower bounds, lower bound and upper bound of the ReLU activation are actually linear bounds. So we can just plug this into this inequality, so that we can actually merge the W3, the weights W3 with the slope and the bias and whatever. And you eventually, if you rearrange all the terms, you will get a linear equation like this. So here we have a diagonal matrix here, which represents if we are selecting the lower bound or the upper bound of the relaxation based on the sign of the W3 matrix. I know this part can be a little bit tricky, so if you have questions, you can ask now. I will pause for 1 second. Okay, cool. If there are no questions, the next thing is after you propagate the thing through the red layers, we have this linear inequality. And after we get this linear inequality, we found that we have the D matrix, and D matrix depends on the sign of W3, and also the inequality you propagated before the red neuron. So after you can determine the D matrix by doing that. So next we have a linear layer which can be done similarly as before, but just plugging the definition, we propagate through the linear layer, and have another ReLU layer. We still apply the same ReLU relaxation and form another D matrix and to still maintain the inequality. And we have another linear layer which can be done quite easily as well. And now we propagate through from the output to the input. Here, if you look carefully, we actually get a bound for the output of the function with respect to the input. And everything before x here is actually just a set of matrix products. So you can actually do a matrix multiplication, put all the things together, and that's the coefficients between x, and that's the linear function we want to get. So the Cron linear bound basically says that for any x within the perturbation set C, the fx is greater than a linear function on x. So and the linear function has the coefficients a and a Bayes term c, and a and c are just the weights, just the functions of neural network weights. For example, the a can be calculated by just doing a matrix product of all the terms. So in that way, you actually get a linear lower bound of the function. Graphically, it just looks like this. You have a nonlinear function fx, and now I found a linear lower bound for fx within these perturbations at C. So everything we derived only valid for the perturbations at C. That's what we want to know. We want to know the minimum within this perturbations at C. So this linear lower bound is only needs to be valid within this perturbations at C. And to find the mean value of the linear lower bound, it's actually a quite easy problem because you just need to do the minimization over a linear optimization problem. So here the C can be, for example, in the 1D case, it's just a segment on the x-axis. And actually, if your C is a LP norm ball, even a high dimensional LP norm ball, you can still write a closed form solution for the F star, for the lower bound of F star. And actually, because this is just a linear optimization problem, we can actually also handle the case where C is actually non-convex. For example, in our paper, we do handle the situation like C it's a more complex perturbation like synonym replacement in some natural language processing task. And we can also handle such as sparsity constraints like a L0 norm constraint, because this optimization problem is just a linear optimization problem. Solve these things are quite easy. And to summarize, what we're doing here right now is just to propagate linear inequalities through the network. And eventually, we will get a linear lower bound for the function. And then we solve the minimization problem just over the linear lower bound, which is quite simple. During the propagation, the tricky thing is we need to deal with the ReLU neuron, but I show you we can do that by using linear relaxation of the ReLU neuron. And after you get a lower bound of this function, if this function is greater than 0 in the binary classification setting, you know the verification is successful. So you know no matter how you change the input within the perturbation set C, the worst case value is also going to be bounded by the F star Cron, and this F star Cron can be efficiently computed by just doing a bunch of matrix multiplications. So that's the first part of the algorithm. And the second part, we extend this bound propagation algorithm to a more general setting. And also we develop the library to help users to use it. So we just talked about how to propagate the linear inequalities on just a simple feed-forward network. But if we have a more computational graph, which defines any arbitrary neural network or any arbitrary computation, we can actually always do the same. If we can linearly relax all the nonlinear operations, such as ReLU and exponential, and we can also propagate the linear inequality from the output start with the identity to all the layers until we reach the input. The input of the computation graph can either be the data, for example, an image, or actually it also includes the weight. Actually, the weight, neural networks weights are also input of the function of the graph we're looking at here. So if we propagating everything through the entire network, then we can get the linear relationship between the output to all its inputs, including data or the weights. So by doing this, we can actually do robustness verification for any complex network such as ResNet, DenseNet, and transformers and so on, but just following the same principle. But of course, to deal with each activation function and implement the entire thing is actually non-trivial. So what we actually hope is we can provide a user-friendly interface for our boundary propagation algorithm for any computation. For example, a user can have a DenseNet, fairly complicated network or a transformer, and the user just define the model here and as euro. So in a PyTorch, in a forward function, define the model. And what our library is doing here is you wrap your model around our library. And we have an object called bounded module, and you can define the perturbation. For example, you have LP norm perturbation, and we have a special tensor object called bounded tensor, which actually defines a perturbation range. It's just of a single value of the tensor. And you can actually use our library to directly compute the bounds for you. More realistically, consider like we have a 3-class classifier with dog, cat, and panda. And your network can be absolutely complex, and you define the network as a computation graph. And the input of the graph are the data and also the weights. And the output is a scores for each class. For example, cat is the top one class prediction here. And what our library can tell you is that suppose we perturb either the weights or the inputs around its original value. For example, if we perturb the input x0 around a L infinity box, we can tell you the guaranteed score range, lower and upper bounds for each class. For example, if you look at this case, the cat can be, the score for cat can be between 2.3 to 4.5, and dog can be minus 0.8 to 1.2, and so on. And in this case, you can see that actually the worst case lower bound of cat is 2.3, but the worst case upper bound of dog and panda are all less than 2.3. That means that we can guarantee that cat stays top one under the input or weight perturbations. So this is what our libraries can give you. If you want to know how your network behave under these perturbations, our library can directly give you this lower and upper bound. So you don't need to implement the entire bound propagation process. We have done that for you. And we actually do have a Colab demo if you are interested in using our library, and you can just follow this link, and we have ResNet 18 example on CIFAR 10, where you define a ResNet 18 model and define the input and input perturbations, and we can compute the bounds. And all the implementations are efficiently done on GPUs, so actually it can be done fairly quickly without relying on any expensive like LP or MIF solver, and you get a valid bound. So that's the second part. Any questions on this part?
I have a quick question. You mentioned that the weights of the model could be perturbed in addition to the input.
Right.
What's the application of perturbing the model weights? I don't think I've heard of that.
Yeah, this is kind of like an interesting setting. When you perturb weights, some interesting things can happen. Like for example, you can actually see how flat the optimization landscape is by plotting the weights and see how the objective change. If you have, for example, a very flat local minimum, and then actually when you produce the weights, the output bounds should be quite small. That's just a hypothetical setting. I don't, of course, I don't know if this is really useful for applications, because for applications, we still care more about the data preservations. You're right, yeah.
I see, cool.
But this is just a theoretical framework. Actually, we can consider either weights or inputs together, because there is no difference on the computation graph. They're just the inputs of the computation graph. So we can consider them together.
I see. Thank you.
Yeah, thanks. That's a very good question. And for the next part, I will introduce how we actually tighten this lower bound, because all the bound propagation process gives you a lower bound for the network output. And there is the potential to make that bound even tighter. I will show you how to do that. When we relax these ReLU neurons, we found that actually lower bound has flexibility. For example, all the string lower bounds here are actually valid for this ReLU function. Because you just need to lower bound the upper this ReLU function. You can choose any slope. This line can have a slope between 0 and 1. You can adjust it. So for each, if you, for example, if you choose this blue line as the lower bound, and you compute the crown bound, and you actually you can get a value for the bound. That's a valid bound, and that's valid sound bound. If you choose the dark green line as a lower bound, you can compute another value of the bound. The two values can be different. They're both valid lower bounds, but the values can be different. So then we have the idea of we can actually try to optimize this lower bound to get the tightest possible bound. The idea is like this. So originally we have this linear function of Cron, and we know that the coefficients A and C are actually a function of neural network weights. But here we also know that they are a function of alpha, where alpha is the slope of the lower bound. Here we have the slope of the lower bound denoted as alpha. And actually for each unstable neuron, you have an alpha, and we can denote all the alpha as a vector here. And we can actually maximize over this alpha to get the tightest possible lower bound. For example, if we just apply the crown bound propagation algorithm for a arbitrarily chosen alpha, then you get a lower bound, for example, for alpha equals to 0. And you can actually find a better lower bound if alpha is 0.5. So this is closer to the fx function, and you're gonna get a smaller lower bound after you solve this linear optimization problem. So this actually gives us a good opportunity to make the bounds even tighter, because we can optimize over all the alphas for all the unstable neurons. Actually, for large networks, there can be thousands or tens of thousands of alphas we can optimize, which in practice actually improves the things quite a bit. So and how to optimize that? We can just run gradient ascent, right? Because we implement our algorithm, bound propagation algorithm, for example, using PyTorch, and alpha is just a part of the implementation, part of the bound computation process. And you can just take the derivative of the final bound with respect to alpha, and you choose, in that way you can choose the optimal lower bound for each ReLU neuron, and you make the relaxation and so that you make the relaxation optimal for your specific network. In our test, we actually found that they can do better than a more expensive LP verifier. For example, if I just formulate the problem as a MIP problem and relax it using a linear programming problem, and throw the problem to an LP solver like Ruby, and we get a lower bound, something like this. And if you apply cron, initially we are actually getting a weaker bound than LP solver. But after you optimize all these alphas, interesting happens after you just do it for a few iterations. we can actually quickly converge to a solution that is better than a LP solver. So one thing that is a little bit tricky here is we not only can optimize this slope of the lower bound, we can also optimize these pre-activation bounds and L and U, because in our algorithm, this L and U are also computed using Cron recursively, because they're essentially also lower and upper bounds just for the intermediate layer. And we can also use the Cron to compute that lower and upper bounds for the intermediate layer. And that bound can also be optimized to make them tighter. So essentially, you're not only choosing the optimal slope, you are also makes this relaxation tighter. If you see the relaxation area as the blue region here, then you see here the blue region is much smaller, so we get a more accurate solution. So that's this part where we use optimization to tighten the bounds. Any questions on this? And finally, the last part is we combine our bound propagation approach with branch and bound. We know that Cron is actually an incomplete verifier, and it only computes the lower bound of the function of this optimization problem. And there are many situations when your network is too large. For example, there are too many unstable neurons, and the relaxation is actually quite weak. And you get a lower bound that's much less than 0. And there's no way for you to improve that. So you can optimize the lower bound slope I just suggested, but after you do the optimization, if the lower bound is still less than 0, then you don't know what to do. So you cannot verify the problem. For last part of my talk, I'll mention how we use branch and bound to actually improve the lower bounds. So we can do a sort of like an iterative refinement and to improve the lower bound a little bit each time until it becomes positive, such that we can prove that the model is robust. And theoretically, we can actually show that lower bound can converge to F star if you have an infinite number of branches. So how branch and bound work here? Let's recall that the ReLU neurons have 3 cases depending on the pre-activation bounds. So ReLU neuron can be a linear function or 0 function, or a unstable case. It can be either of the 2 cases, and you have to do relaxation to handle that case. And that makes the bound loose, because for this case, the 2 linear bounds are not the original ReLU function, they're just the bounds. So you get the relaxation here that makes the entire thing loose. So, but if we can, what we can do is to split each unstable neuron into 2 subproblems. For them, if we have this unstable neuron, we can split it into 2 cases. One is active, one is inactive. For both of the cases, they're linear. So that means that if we split the original problem to 2 independent subproblems, in each subproblem, we have 1 less unstable neuron. So we have 1 less relaxations needed. So in each of the 2 cases, actually the neuron becomes a linear neuron. And in addition, for each subproblem, you need to add the so-called speed constraint, because in this setting, you have to constrain Z1, for example, to be greater than 0. And for the second case, you constrain Z1 to be less than 0. So after you're adding this constraint to the formulation, and you have 2 subproblems, you can actually combine the 2 solutions together to get the solution of the original problem. So for example, here, if the original lower bound computed is a negative number, -3, and I can split a certain unstable ReLU neuron and split it into 2 cases. So for this case, by adding this Z1 greater than 0 constraint, we actually get a tighter lower bound, -2. And for this case, for Z1 less than 0, we get an even tighter lower bound, 0.2. And we know actually in this case, if Z1 less than 0, the subproblem is already verified because lower bound is greater than 0. And for the case Z1 is greater than 0, the lower bound improved from -3 to -2 is still a negative value. But fortunately, we can still further improve it by branching on another neuron. So until the lower bound for all the subproblem becomes positive. So it looks like this. Suppose we have 4 unstable neurons, Z1, Z2, Z3, and Z4, and we can branch them in any order, but let's just suppose we branch on Z1 first. And we got 2 subproblems. One of them is already verified. And here the lower bound improved from -3 to the minimum of the 2, that's actually -2. So improve the lower bound from -3 to -2. And after we branch on the second unstable neuron, and the lower bound becomes -1 and -0.5. And both of them are still less than 0, so we cannot remove them from the problem. We still need to branch both cases. The lower bound improves from -2 to the minimum of the 2 values, which is -1. And we branch on each of the neurons for using unstable neuron list 3 and the bounds further improve. And we have 4 cases, but 3 of them actually can be deleted from the problem because they are already verified with a positive bound. And finally, after doing branching on the last neuron, all the subproblems have a positive bound. So actually, we have a lower bound, global lower bound of 0.1. That means the problem is verified. So that's how the branch bound process works. And by doing that, as you can see that we can by doing the branching, we are improving the lower bound more and more. And theoretically, we can show that actually we can eventually lead to the optimal value f star to as a complete verifier. So that gives actually a great power. So for example, for branching, for computing the lower bound on each subproblem, we can just use the shaper method such as cron. But just by doing enough branching, we can make this shape method to achieve completeness and increase its power over time. So if we do have a lot of time, we can run a lot of branching, and we can improve the bounds a lot by just branching a lot of unstable neurons until it reaches a positive lower bound. So the contribution of our approach is that we combine this very fast bound propagation methods on GPUs with branch and bound, and to achieve 3 to 4 orders of magnitude speed up. And because we run everything on GPU, as you can see here in the branch and bound search tree, there are actually a lot of subproblems we can also solve in parallel in a huge batch on GPUs, so which can be done quite efficiently. And for each of the nodes, we use cron to compute their lower bounds, and we can compute bounds of a couple of nodes together by packing them into a batch and just compute all the bounds together on GPUs. This is different from the branch and bound procedure used in MIP solver, because MIP solver also uses branch and bound, but the issue with MIP solvers is they don't have this very efficient bound propagation process. They also cannot run things on GPUs easily, and they don't really know the problem is a neural network, so they cannot apply our specialized algorithm to this problem. So, but one minor trick we use during the branch and bound is that, as I mentioned, to do branch and bound, you have to use this split constraint to see this neuron is less than 0 or greater than 0 to split the ReLU neuron into 2 cases. But the bound propagation algorithm currently still do not support this constraint. But we show that by just doing a simple modification, we can use a Lagrangian function to handle this split constraint. For example, we have a neuron, we want to make the neuron negative, and we can just add a Lagrangian with a multiplier beta here to handle this constraint, this minimization problem with this constraint. Because we only need to get a lower bound of it, so it is okay. As long as we take any valid beta greater than 0, we get a lower bound of the original problem. And actually, this only needs a small modification of the bound propagation process. Because you can see here in original cron bound, the linear relationship is W3D2, but here we just need one additional term involving beta. That's all we need here. And we can propagate the bounds similarly. And finally, we get the beta cron bounds. We all have the coefficients A and C, and also terms with beta. And you can choose any value beta greater than 0, and similar to what we have done for alpha cron, where you have alpha parameter to optimize. Here you have a beta parameter to optimize, and you can choose any beta between 0 and 1 to get the tightest possible bound. So that's the last part of the algorithm. Any questions on this? Okay, cool. Now finally, I will show you some benchmark results, including our results from the VN computation. First of all, we evaluate our algorithm on a small benchmark used in many verification papers. This benchmark is it has 3 models with 100 pre-selected test images each. So these images are pre-selected so that it can handled by current verifiers, because many verifiers are slow. So if you just throw a big model as a benchmark, then many verifier actually doesn't work. So this particular benchmark was developed with relatively small models and also easy instance to verify. And each method need to verify each image within a 1 hour timeout, and each method wants to solve to verify the as many instances as possible. So let's see the results. So here we plot the number of verified images versus time. The time is in log 0, and the timeout is about 3 hours, and everything is cutting off here. So if you, for example, if you just run the MIP solver, the curve looks like this. So MIP solver takes over a few hundred seconds to solve the first image, and after an hour, it solves only 30% of image. There are already other verifiers which can improve over the MIP solver, and you can see here there are many other baselines, and this green line is our verifier, alpha beta chrome. By combining this offline bounds with alpha and beta parameters, and also we're doing a branch and bound on with bound propagation on GPUs. And we actually found that this benchmark has become too easy for us, because we can actually solve 90% of instances within just 10 seconds. So within 10 seconds, we solve over 90%. So, and if you just run MIP solver, we are like 2 to 3 orders of magnitudes faster. And this benchmark is too easy, so we also tried a more challenging benchmark, where it is where we want to verify adversarially trained models. So we know adversarial training is a practical way to get you a robust model. So in case you don't know, adversarial training just find adversarial examples during training, and through the model, through all the adversarial examples to the model, so the model is trained with the adversarial examples. But these adversarial examples are found by some heuristic attacks like projective gradient descent. So you don't really have guarantees on the robustness of the model, although practically it looks like they're robust. So a strong verifier should also give a theoretical guarantee for some of the tests, for at least some of the test images that looks robust. So for example, if we have 100% test images, and some of them are classified incorrectly, we ignore them. And for the classified correctly images, we have, with some of them can be attacked. So these images are not robust. And some of them cannot be attacked, which are inside this blue box. And for the images that you cannot attack successfully, some of them can be verified. That's a verified accuracy. And there's a gap between the verified accuracy and the empirical robust accuracy found by attacks. And there are some images where you don't know if they're robust or not, because you cannot verify them and you cannot also attack them. And there's always a gap between the empirical robust accuracy and the verified accuracy. So our method actually can close the gap between the verified accuracy and empirical robust accuracy. See for MNIST example, this is a relatively small network, and you can see that this blue box here, blue bar here is the upper bound of the robust accuracy by some attacks, which is basically the empirical robust accuracy. And the green box is the number, is a percentage of images we can verify. We can actually verify they're robust, and there's only a very small gap between the two. And before our work, so the best method work before is based on semi-definite programming. Semi-definite programming is better than many other formulations like linear programming, and also Cron. If you're just using Cron without branch and bound, it looks pretty bad. You can verify very little images. And the only promising method before was the semi-definite programming. But our approach just significantly outperforms semi-definite programming, and we also run much faster. We can do all the things within just 1 minute. If you do semi-definite programming, it takes actually 2 hours to solve just one single image. And both approach actually use GPU. This semi-definite programming approach are also GPU accelerated, but they still need 2 hours. For a larger CIFAR network, which has around 15,000 neurons, you see we still have a clear benefits here, but although the gap here is still large, and we still need to further closing this gap using better methods. So I saw some questions in the chat. So maybe let me just quickly finish the last part of my presentation, and I will deal with the questions. So finally, results for the weighting computation. So each year we have a verification of neural network computation, where many teams from different universities across the globe participate, and each team submitting their tool to the organizers, and the organizer evaluates each tool in a standardized AWS environment. So it's gonna be fair for everyone, and it's running on a common set of benchmarks. So there are 8 benchmarks in last year's competition, and the benchmarks come from different backgrounds like image classification and also control and database. But anyways, they're formulated as a verification problem where you have a function where you can optimize. Just the function is defined differently in each scenario. And each benchmark contains tens to hundreds properties to be verified. And each property has a timeout, and each tool tries to verify as many instances as possible within the timeout threshold. And the max score for the competition is 800. That's 8 benchmarks by 100 points for each benchmark. So that's 800. And there are 12 teams in last year's competition, and they're from different universities internationally. And if you just look at scores, we are getting a close to 800 full score, and the gap between our first our two and the second place and third place, I say the gap between the score is large. That means our algorithm has a clear benefits. If you just take a look at each individual benchmark, then you'll see that we can verify the most number of problem instances for all the benchmarks. For some easier benchmarks, everyone can do very well. But for some harder benchmarks, you can see actually there is a gap between our approach and other approach. So that means our bound propagation based approach on GPU with branch and bound actually has a great benefit on doing the neural network verification. So I have to acknowledge that this tool was built by a team from not just CMU and also from Northeastern, Columbia, and UCLA. Without all my collaborative effort, we cannot do such a good tool for verifying neural network. And if you are interested, you can check out our tool for neural network verification by visiting abcronk.org. And we have many instructions and examples to help you to get started. If you have some certain application where you want to verify some properties of your network, not just robustness, in some other cases, you can also formulate a problem. If you can formulate your problem as an optimization problem similar to ours, you can use our tool to do it. And finally, I have to say, although we have made a great success so far by having a 2 to 3 orders of magnitude improvements compared to the MIPS-solver-based approach in 2017, we still have a long way to go, because even for the competition, for example, most of the networks are relatively small. They have maybe like the largest one is around maybe 50,000 neurons or something like that. It's still relatively small compared to the ImageNet or like vision transformers we're using right now. We do need better branching and better bounding approach to further scale things up. we still need like 100 times more scalability. Although we have done 1,000 times improvements compared to approach in 2017, we still have a long way to go. And another interesting thing I'm thinking about is like, how can we train a network to make it easier to verify with branch and bound? Because we just train a network with cell training for them, it knows nothing about branch and bound and probably won't produce a branch and bound friendly model. And also this question on what's the best neural network architecture for verification? Actually, certain neural network architecture are not good for verification. For example, for in vision transformer, we have a attention layer. The attention layer can be a trouble because it's a highly nonlinear operation, and it's hard to do a linear relaxation over that operation. So you get pretty loose bounds over that. So we need to handle these cases as well. And also, I also worked on verification of other types of machine learning models, such as trees and k-nearest neighbor. And these things can also be have similar robustness guarantees. And maybe it's possible to combine neural networks with this type of model to further improve the verification performance. So that's the end of my talk. And thank you for attending. And if you have a chance, you can check out our verification tool. And we also hold a verification tutorial at AAAI 2022. If you happen to attend this meeting, attend this conference, you can just drop by our tutorial if you're interested. Okay, thank you. And I will happy to answer any questions now. So there's several questions from the chat. Maybe I can look at this first. So if all nodes in the question says if all nodes in the network are stable, then is the verification with incomplete verification method the same as what we get from completion verification methods? The answer is yes, because if all the nodes in the network are stable, that means every random neuron becomes a linear function. Actually, that means the entire network actually is just a huge linear network. In that case, incomplete and complete doesn't matter because you can always solve to the global minimum on a linear function. That's the answer to the question. So another question, what if you have a nonlinearity like normalization or projection layer? That's a good question. So technically, we can handle every possible activation by just finding a linear lower bound and linear upper bound for the activation function. So suppose you give me any function, it can be a high-dimensional function, not necessarily a 1D function. For example, we can give me a max Boolean, whatever, the input can be multiple numbers rather than just a single number like ReLU. So we can actually find the linear lower hyperplane and the linear upper hyperplane for this function, for any nonlinear function. As long as you can linearly bound that function, that actually the entire thing actually works. For normalization, I'm not sure what kind of normalization you are talking about. Like if you're talking about batch normalization, actually batch normalization is just a linear function at inference time because we already have this mean and standard deviation statistics during inference time. You actually don't update them, so it's just a linear function for doing normalization. So it's just like a linear layer. There's no relaxation needed. And the projection layer, I'm not sure. Actually, I'm not exactly sure what kind of projection layer here. But assume as long as you have the exact formulation of the projection and you can bound the function with the linear lower and upper bounds, you can do it. But just it's not always optimal. So as I mentioned, there are some cases where the linear bounds can be quite loose. For example, if you have a tension layer, so that's the troubles we had before. And in that case, I would suggest to use some other functions that are easier to bound linearly in order to get a highly verifiable network. If your goal is to get a network that with formal guarantees, if you want to get these guarantees, then you should make your network a little bit more verifier friendly.